In this module, so far what we have done is we have introduced the concept of particles at interfaces, and we have looked at several applications where this concept can be exploited, and we discussed characterization of particles in the context of when they are at the interface, and we mentioned that an additional characterization one has to worry about, and we discussed about contact angle measurements, which is a method of finding out what is the equilibrium position of particles with respect to the interface. What we will do in this lecture is that we will look at some important experimental observations, and these experimental observations enable us to make two interesting points. Okay. One is that electrical double layer interactions or the electrostatic interactions are modified when the particles are at interfaces, and number two is that some of the experimental observations can be used to discuss what is called as stability of colloids at interfaces. We will discuss some of these observations, and we will think about mathematically deriving some equations which enable us to make these statements. And the first result that I am going to show is the work, seminal work of Piransky. We are looking at the microstructure of particle-laden interfaces. In these experiments, what was done is there is a small container, and that container is filled with a colloidal dispersion, what is highlighted now, and in this container a very dilute dispersion of particles was placed, and this is a dispersion of polystyrene particles in water, and the size of the particle is 245 nanometer in diameter. And naturally, when you do not have anything at the top, so you will have air, therefore, there is an interface between water and air, and what you see here is a schematic of a microscope objective, and you can move this objective up and down so that you can focus at the interface and look at the microstructure of the interface containing these particles. And there are two distinct microstructures that can be seen here. So, if you look at the image, you see these small dots, and these are the particles of 245 nanometer diameter. And if you take a closer look, you will see that every particle has 6 neighbor. For example, if I look at let us say a particle here, there is one neighbor there, 1, 2, 3, 4, 5, 6, right. So, therefore, every particle has 6 neighbor, and it appears that the distance between, if I were to draw a line, okay, you will see that you will see peaks and valleys, and the distance between the peaks corresponds to the particle position, and looks like they are periodically spaced in figure A, and therefore, this microstructure resembles a crystalline arrangement or an ordered arrangement of particles. On the right, figure B is obtained by doing a similar experiments. The only difference is that the concentration of the particles at the interface is lower. So, in the context of surface fraction or the fraction of the area that is occupied by the particles, it is higher in the case of A, and it is slightly lower for the case of B. And if you look at image B, the particles are not as ordered as what you see in A, and so this corresponds to a liquid like microstructure, or in this case the particles are disordered. Okay, so these are the experiments with very tiny particles, that is 245 nanometer particles, and these are the microstructure at water air interface. And what you are seeing now is a microstructure which is obtained by depositing 3 micrometer polystyrene particles, and they have a zeta potential of minus 85 millivolts. They are highly charged, and the fact that zeta potential is minus 85, that means they are negatively charged particles, and the charge density that is corresponding to this zeta potential is 6.7 microcoulombs per centimeter square. Okay, and these are deposited at water decane interface. Again, similar features can be seen. The monolayer is crystalline, that means if I were to draw a line like this, you will see that the interparticle spacing between the particles is very similar, and every particle has except for some small dirt, you see that every particle has 6 neighbors. For example, if I look at this, so I can beautifully draw a nice hexagon, right. So therefore, there is a non-close packed hexagonal arrangement of particles at the interface. Now, these two experiments, the conclusions that one can draw from these two, the microstructure that we have discussed so far, is that so you have two particles and you can designate the interparticle separation by this d, the separation distance d. What is evident is that the particle monolayer is homogeneous. What I mean by that is, if I look at any region of the monolayer, whether you are in one corner or in the other, or anywhere across the monolayer, the monolayer looks homogeneous. That means the particles are uniformly distributed all through the available interfacial area. The second conclusion that one could draw is that interparticle separation distance, okay, that is d, okay, is much larger than the diameter of the particles. Okay, that means if I look at so these particles are 3 micrometer in diameter. Now, if I look at the interparticle separation distance between the two particles, it appears that the interparticle separation is at least about 2 times the particle diameter, or more, depending upon the concentration of the particles that one works with, and the fact that the interparticle separation is much larger than the diameter of the particle, it suggests that the interactions must be repulsive, and that the interactions are long ranged because of the fact that the separation distances are at least 2 times the particle radius or larger. That suggests that the interaction between the colloidal particles are repulsive and they are more long range. Now, let us look at comparing the particles in the bulk versus particles at interfaces. What is the difference? Now, so we discussed that when you have charged particles dispersed in a fluid, there is going to be an electrical double layer that is formed. The first thing is that the moment you have a charged particle dispersed in water or any other fluid medium, if there is going to be dissociation of charges, the particle is going to acquire some charge, right, and whatever ions are present in the vicinity of the charged particle, they are going to rearrange and they are going to give an electrical double layer, right, and that electrical double layer is depicted here. So, you have a Stern layer, and there is a surface of shear, and there is a electrical double layer thickness associated with the thickness of the double layer, and you have a Stern layer where the counter ions are closed or tightly bound to the particle surface, and you have a diffuse layer where the concentration of counter ions varies with distance from the charged surface, right. And for such a configuration, the interaction between two spherical particle is given by these two expressions. The first one is for a case where the Gouy-Chapman theory has been used for the overlap of the electrical double layer, and the second one is for the case where we have a Debye-Huckel approximation, which is valid when the zeta potential is of the order of 25 millivolts, right. Now, this is the picture that we have in the bulk, that is the overlap of the electrical double layer gives rise to electrostatic interactions or the electrical double layer interactions. One thing that is important to notice is that around the particle, since this is a particle, around the particle the electrical double layer is symmetric. Okay. Now, if you look at the particle sitting at the interface, what is shown here is a schematic of particle 1 and particle 2, and they are sitting at the interface between the two fluids, and this is a negatively charged particle. Okay, that is the charges that are on the particle surface, and you have the counter ions that are depicted here. And one thing that is to notice is that the electrical double layer or the distribution of counter ions around the charged surface is not symmetric anymore. Okay, that is because the dissociation of the charges, occurs only across the surface that is in contact with water. That means, so although the particles would also have the surface charge groups, in the surface, on the surface that is in contact with oil, the dissociation of the charges requires a suitable medium, and a charge like, say for example COOH would dissociate when it is in contact with water and under appropriate conditions, and therefore the dissociation gives rise to COO minus and H plus only in the region where the particle is in contact with water. Okay. Therefore, there is an asymmetric distribution of counter ions in the case of particles at interfaces, and this difference is what is giving rise to long ranged interactions in the case of particles at interfaces. Now, this is a schematic that there is a dissociation of charges only on the water side. Now, what one could do is that because of the fact that the charges on the particle surface and the counter ions in solution, the fact that the charge density that is arising because of the charge density corresponding to the dissociation that occurs on the particle surface and the total number of counter ions in solution are going to be exactly same. Therefore, we can associate a charge minus q with the particle surface, and similarly for the ions in the double layer we can associate a charge plus q, and a typical length scale by which these two charges are separated is of the order of Debye screening length, that is kappa inverse. Therefore, so for every particle that is at the interface there is a dipole. Okay, that is the dipole corresponding to particle 1, and that is a dipole that is corresponding to the particle 2, and these dipoles, depending upon what convention you use, they point in the same direction and they are along the axis that connect the center of the two particles, right. So, that means if they will be pointing out in this direction, right. Maybe I can just quickly redraw. Okay, so they will be pointing in the same direction and they are along the axis that connect their centers. Okay. Now, whenever we have two charges that are equal in magnitude, but opposite in sign, we can define a dipole moment q, which is given by q times kappa inverse, that is mu, right. And now, the force of repulsion between the two dipoles is given by, if you have two dipoles mu 1 and mu 2, the force of repulsion is given by mu 1 mu 2 divided by 4 pi epsilon naught epsilon r into r square, where r is the separation distance between the two dipoles. And if this expression can be written if the separation distance r is much greater than kappa inverse, and because the dipoles are of similar magnitude, therefore, the numerator becomes mu square, and in the denominator you have 4 pi epsilon naught epsilon r into r square. And because of the fact that so this is the expression for the force, and the force is the negative gradient of the potential. Therefore, if you want the repulsive potential or the electrostatic interaction between the two particles, I need phi of r, which I can obtain by integrating this from d to infinity, and where d is the distance of separation between the two dipoles, and it can vary from d is equal to 0 all the way up to d is equal to infinity, right. So, therefore, if we work this out, what you have is mu square 4 pi epsilon naught into epsilon r, integral of 1 over r square is minus 2 divided by r cube, and that goes between the limits infinity and r is equal to d, and because r cube is in the denominator, the this term at infinity is 0. Therefore, phi electrostatic essentially is given by the 2 and the 2 gets cancelled. Therefore, the phi electrostatic is given by mu square divided by 2 pi epsilon epsilon r into 1 over d, and because we have defined mu as q times kappa inverse, I can substitute for mu in terms of q and kappa inverse. So, therefore, we can write this as q divided by sorry, this is going to be q times kappa inverse, right. Okay, this is q times okay, this is kappa square, right, because kappa minus 2, right. Q, this is q times kappa minus 2 in the numerator, that is kappa minus 2. Therefore, and this charge q would depend on the total number of charges that are dissociated, and you can write this q as z times E, where E is the charge in the electron, and z can take any value depending upon the total number of charges that are dissociated. If for example, if you take a case where you have a particle that is sitting exactly with half the surface in contact with oil and water, in that case, and if the total number of charges on the surface is like, say for example 3000, then this q would become 1500 times E, okay, something of that order. Okay. So, therefore, phi electrostatic goes as 1 over distance to the power of 3 as against e power minus kappa times d for the case of interactions, colloidal interactions in the bulk. So, and this 1 over d cube dependence is what gives rise to the long range nature of the electrical double layer interactions compared to the similar interactions in the bulk. Now, the other observations are that so when the particles are trapped at the interface, similar to when they are in the bulk, the particles continue to exhibit vigorous Brownian motion, very similar to the particles in the bulk. And it is also observed that once they are at the interface, I mean, if you imagine this to be at the interface, and if you have this is in a petri dish, for example. Okay. So, now the particles, they never penetrate into the bulk. That means, once they are sitting at the interface, once they are adsorbed at the interface, they continue to exist at the interface and they never go back into the bulk. And moreover, if there is the particle that is coming in the vicinity of the interface, and experimental observations show that they can be drawn towards the interface, and they can that means the transfer from the bulk to the interface is possible. However, the transfer from the interface to the bulk is practically impossible. Okay. This suggests that polystyrene particles are irreversibly stuck at the interface, and the fact that they are irreversibly stuck points to the fact that the particles are trapped at the interface in a energy that is much deeper than the thermal energy. So now what we will do is we will try and calculate what is the depth of the energy well in which the particles are sitting at the interface. So we are going to do that by doing a very simple surface energy balance, which is I am just going to follow this reference for doing that. So this is a schematic of like say a polystyrene particle in this case, which is sitting at the interface between air and water, and theta is the contact angle, and so the radius of the particle is r, and the center of the particle is at C, and Z refers to the location of the it's a vertical distance that will tell us what is the location of the particle with respect to the interface. Z is equal to if I scale Z with r, okay, that is the radius of the particle, then I will get Z bar, and this Z bar is going to be plus 1 when the particle is in is completely in air, and Z bar is minus 1 when the particle is completely in water. Okay. So, so now if you have a configuration like this, now so when the particle is at the interface, right, and initially imagine that there is a water air interface, and you bring a particle either from the upper phase or the lower phase, and then you position them at the interface. Now, if you look at such a process wherein you bring in a particles from one of the phases and position them at the interface, so what is done is that we have replaced in this configuration, we have replaced water air interface, okay, with two new interfaces, right. So, if say that this is the water air interface that was originally present, and the fact that you have placed the particle at the interface, you have created two new interfaces, that is the interface between the particle and in this case air, and the interface between particle and water. We have created two new interfaces, and we have removed the water air interface which was originally present, and therefore, the total surface energy when a spherical particle is at the interface is given by the summation of the three interfacial energies. One is the surface energy of the particle air interface. Second is the surface energy of the particle water interface, and these are the surface energies that were newly created and they take the positive sign. And however, we have replaced the air water interface, that is the energy of the missing interface, that is negative because that has been lost. And so for and the fact that the surface energy is given by surface area multiplied by surface tension, you can write down the individual contribution to the total surface energy, and this term is the E for the particle air interface, this term is E for the particle water interface, and this is the E term for water air interface. And if you look at the schematic, so we see that and we said that this distance is 1 plus z bar, and therefore, the total interfacial area that is available, the total particle air interfacial area is given by 2 pi r square times 1 plus z bar, that is the particle air interfacial area, that multiplied by the particle air interfacial tension or the surface tension will give me the surface energy that is associated with particle and air interface. And the second term, this 2 pi r square times 1 minus z bar, okay, that is this distance, this is 1 minus z bar is this distance, that multiplied by 2 pi r square will give me what is the surface area of the particle water interface, that multiplied by the corresponding interfacial tension will give us what is the surface energy of the particle water interface. Now, this pi r square into 1 minus z bar tells us what is the interfacial area that has been replaced, and that multiplied by the interfacial tension between water and air will give us the contribution of the water air interface to the total interfacial energy. In this expression, this z bar is z by r, that is the scaled vertical distance of the center of the particle C with respect to the air water interface. Now, you can divide. So, now if you look at, so you have r square term that occurs in all the terms, and because of the fact that gamma water air is a interfacial tension of the water of the two immiscible fluids that are considered, and it does not depend on any particle that one considers. Therefore, we can scale the total energy as by gamma water air multiplied by pi r square. Therefore, E bar becomes, this is the ratio of the particle air interfacial tension divided by water air interfacial tension, and this is the particle water interfacial tension divided by water air interfacial tension. Therefore, and if we designate this as A and this as B, this E bar becomes A multiplied by 2 times 1 plus z bar plus B multiplied by 2 times 1 minus z bar minus 1 minus z bar whole square. Now, because of the fact that A and B are known, that is, if we take typical these A and B values, which are the ratio of the interfacial tension of the particle air with respect to interfacial tension of air water, and the polystyrene, because of the fact that we have considered polystyrene particles, the polystyrene air and polystyrene water interfacial energies are known, and water air interfacial tension is 72 millinewton per meter. So, therefore, we know what is the value of A and B, and this z bar can go from +1 to -1. So, therefore, I can plot this E bar as a function of z bar, and what is interesting in this expression is that there is a minima at some location. It's a this variation suggests that there is a energy well, and we can actually calculate the positions corresponding to that minima. So, what all you need to do is take this expression, that is E bar, and we could differentiate this with respect to z bar. So, that is d E bar divided by d z bar, and if we set that equal to 0. So, we get what is z minima, that is the coordinates that correspond to the minimum location, okay, that appears to be b minus a, and because we know what is the value of b, that is 0.14 minus a, that is 0.49. Therefore, this becomes 0.35 with a negative sign, and the fact that the z bar minimum is negative for the considered case, the particle it tells us that the particle is more in air, and looking at this value one could make a conclusion as to whether the particle that is considered is hydrophilic or hydrophobic. So, that means the z bar minimum if it is equal to I mean if the minimum occurs at z minimum is equal to 0, that means the particle is such that the equal halves of the particle are in contact with the two fluids. Therefore, the particle is going to be neutrally wetting. So, therefore, z bar minimum value gives an indication as to whether the particle resides more in the water phase or more in the air or oil phase. Now, and we can rearrange this and then write E bar as z bar square plus 2 times a minus b, z bar plus 2a plus 2b minus 1. And what we could do is we can actually evaluate E min. So, if you want because we know what is the location of the particle with respect to the interface, that is we know z bar minimum, I can substitute the value of z bar minimum in this expression and calculate what is the energy that corresponds to this minimum position. Okay. That means I would have to evaluate this expression, however, by replacing z bar with z bar minimum, and if you substitute for z bar minimum as b minus a, it turns out that E bar minimum is 0.14, and because we have scaled the energy with pi r square into gamma of air water, if we can calculate the absolute value of E minimum, okay, by multiplying this 0.14 with this pi r square into gamma a water, and if we take particles that are like say for example 1 micrometer radius. Therefore, this E bar minimum becomes 0.14 into pi, that is 3.14 multiplied by 1 10 power minus 6 whole square into 72 into 10 power minus 3 in SI units, divide. Okay, therefore, this becomes okay, so that is 0.14 times 3.14 times 72 into 10 power minus 15. Okay. And if we scale this with thermal energy at 298 Kelvin, which is of the order of 4 into 10 power minus 21 joules. Therefore, what we end up with is so this gets cancelled. Therefore, typically the number that you will get would be of the order of 10 power 6 kBt. That means so if you look at the coordinates of the minimum, the coordinates of the minimum give us two important parameters. One is what is the location of the particle with respect to the interface. Number 2 is that what is the depth of the energy well in which the particles are dispersed, in which the particles are trapped. And it turns out that for 1 micrometer particle, this energy depth is of the order of 10 power 6 kBt. And this magnitude of energy, magnitude of the energy well is important because the particles at interfaces are considered as model systems to study colloids in 2D. Okay. And that can only be said if the depth of the energy well is much larger compared to kBt, that is in this case 10 power 6 times kBt. Number 2, it so happens that the particles that are trapped at an interface, that is two dimensional colloidal systems, they exhibit a very high stability. That means if you create an interface containing particles and if you ensure that the evaporation of the fluid is minimized, or or the conditions such that the fluids do not evaporate, and if you work with the clean fluids or the dust free environment, it turns out that the particles at the interface, they continue to remain in the same arrangement for several months. Okay, which is an indication that the particles once at the interface, because of this very high energy well, they continue to exhibit ultra high stability, an important concept which helps us to define the particles at interfaces as a nice model system to look at colloids in 2 dimensions.